At the end of the 19th century, physicists were feeling pretty good about themselves. Looking at the mechanics of the universe, scientists like Lord Kelvin believed the major laws of nature were completely locked down. Everything operated like a perfectly predictable, mathematically sound clockwork machine. Then, scientists started looking closer at the atomic level, and that clockwork broke. They discovered a microscopic realm where energy moved in jagged leaps, and particles didn't have exact locations, only probabilities. To make sense of it, they built an entirely new math, quantum mechanics. Albert Einstein actually helped build that new math, but he hated what it implied. He believed the universe must be governed by strict cause and effect. The idea that reality at its lowest level was driven by random chance, that God played dice with the universe, deeply offended his sense of logic. This disagreement reached a boiling point in 1927. At the Solvay conference, Einstein clashed daily with Niels Bohr, the champion of quantum theory. Bohr argued that at the atomic level, properties like a particle's position simply do not exist until they are directly observed. Einstein refused to accept that. He spent the conference trying to poke holes in Bohr's logic, demanding that objects must have real properties, whether we look at them or not. That standoff ignited a debate that would consume the physics community for decades. 8 years later, Einstein thought he finally had the ultimate kill shot. He published a paper with 2 colleagues, now known as the EPR paradox, designed to prove the quantum equations were missing crucial pieces. His argument focused on an unavoidable quirk in the math called entanglement. According to quantum mechanics, if 2 particles interact and then separate, their properties remain inextricably linked. If you measure one, you instantly determine the state of the other, even if they are billions of light years apart. Einstein famously mocked this as spooky action at a distance. He argued that information cannot travel faster than light. Instead, he proposed that these particles must carry secret instructions, what he called hidden variables, that dictate their behavior long before they are measured. Bohr fired right back, insisting there were no secret instructions. The particles are truly undefined, hanging in a mathematical haze of probability until the exact second someone looks at one of them. For decades, neither side could prove their case. No one knew how to build a machine that could actually test whether the universe was running on hidden variables. The dispute paralyzed theoretical physics, settling into a purely philosophical stalemate. That changed in 1964, when an Irish physicist named John Bell figured out a way to drag the debate out of philosophy and into the lab. To understand his test, look at this setup. We have a central source shooting entangled particles to 2 distant measuring stations, labeled A and B. The observers at each station randomly rotate dials to measure the particles along different polar axes. By recording the results over hundreds of tests, we can calculate a statistical correlation score between the 2 stations. This chart tracks that correlation score. Bell mathematically proved that if Einstein was right, if the particles carry hidden, pre-programmed instructions, that score has a strict speed limit. It can never cross the number 2. But look at the math for quantum mechanics. If Bohr was right, and the particles are truly entangled, HSH inequality gave physicists a clear pass-or-fail equation. Reality was either local and predictable, or it was entangled and weird. In 1972, a young physicist named John Clauser set out to test this. He fully expected to prove Einstein right, but when he fired up his detectors and ran the numbers, his score violated the classical limit. He proved Bohr right. Skeptics immediately pushed back, pointing out potential flaws or loopholes in the experiment. The biggest was the locality loophole. Critics argued the 2 measuring stations were too close together, allowing them to secretly communicate their settings to each other at the speed of light. 10 years later, Alain Aspect closed that gap. He used ultra-fast acoustic switches to change the measurement settings while the particles were already in flight. The stations were changing their dials in 10 nanoseconds, far too fast for any light-speed signal to cross the room. The quantum score held up. Still, skeptics wondered if the random number generators choosing the settings were somehow being influenced in advance. So in 2018, Anton Zeilinger's team closed the freedom of choice loophole. They pointed telescopes at distant quasars and used the ancient light from those cosmic bodies to dictate the dial settings. Other teams tackled the fair sampling loophole, using highly efficient superconducting detectors to prove that missing data wasn't skewing the results. Every single time, the inequality was violated. For 50 years, physicists systematically hunted down every conceivable way Einstein's hidden variables might be hiding, and one by one, they eliminated classical physics from the atomic world entirely. In 2022, Clauser, Aspect, and Zeilinger stood together in Stockholm to receive the Nobel Prize in Physics for a lifetime of work dismantling local realism. Their experiments delivered the final verdict. Einstein was wrong. The universe is deeply non-local. Particles do not hold fixed properties independent of our observation of them. Harnessing these correlations shifted the focus from proving Einstein wrong to building new types of machines. This experimental proof established the field of quantum information science, making quantum computing and unbreakable cryptography a physical possibility. Einstein's 1935 paper was an attempt to destroy quantum mechanics. Instead, his fierce resistance forced the physics community to rigorously define and test the very foundations of the theory. Einstein's rejection of quantum mechanics didn't stall the field, it gave it a target. This century of research shows that we often learn the most about reality by taking our most sophisticated doubts and chasing them until they break.